everyone. So in this video, we're going to be talking about transformations of the graphs of sine and cosine. So transformations is a topic that you should have learned in your previous class, so in your Math 141 or Pre-Calculus 1 class. And basically what we're going to be doing is taking those exact same ideas that you learned in your previous class and just applying them to trigonometric functions and their graphs. So I'm going to be doing a brief review of transformations and a couple of examples of how transformations work on functions that are not trigonometric functions at the beginning of this video. That being said, I am going to be expecting that you've learned this before, that you have learned transformations. We just don't have time in this class to completely from scratch relearn what transformations are. So what I would say is that if you watch the first 10 minutes or so of this video and you feel like it's still not really coming back to you, I'm going to link some of my 141 videos in the description of this video, and I would recommend going and watching those because in those videos I'll go into a lot more depth about why transformations work the way they do. Okay, so what are transformations? The general idea that I like to say to kind of describe transformations is that you're looking at changes in the formula of a function and kind of seeing what those look like in the graph of the function. So what is the connection between making changes to the formula of a function and how those actually look in the graph of the function. So here I wrote down, transformations are changes to the formula of a function that correspond to changes of the graph or to the graph of the function. And what do I mean when I say changes? So I want to get a little bit more specific here. Really with transformations, when you're talking about what are you doing to the formula of a function, you're really only doing three different things. You are either adding or subtracting a number, so addition or subtraction. That's one thing you could do to change the formula of a function. You could also negate something, so negation. So that means multiplying basically by -1. So either making the function as a whole negative or making your input variable negative. And then the last one is multiplication. So you can be multiplying either your function as a whole or your input variable by a number. And so each of those changes that you can make to the formula are going to change your graph in different ways. And so what kind of changes are you going to see in your graph? Well, you could see your graph get shifted. So a shift just means that you're kind of picking a graph up and moving it. You're not actually changing the shape of the graph at all. You're just literally moving your graph around. Another change that can happen to your graph is a reflection. So reflections mean, again, not changing the shape of your graph, but just flipping it over the X or the Y axis. And the last thing that you can do to change the shape of a graph or to change a graph with transformations are stretches or compressions. So that basically means, in this case, that does mean that you're going to be changing the shape of your graph. So that's like making your graph, taller or shorter or wider or narrower, kind of pulling it or pushing it in different directions to change its shape. And so as you might have guessed from the way I color coded this, we know what kind of changes to the formula correspond to what kind of changes to the graph. And so specifically, anytime you're adding or subtracting a number from your function or from the input variable, that's always going to correspond to a shift. Negation will always correspond to a reflection, and then multiplication will always correspond to a stretch or compression. So there's kind of only one other thing that you need to keep track of, which is, are these shifts, reflections, and stretches or compressions, are they vertical or are they horizontal? Right? Vertical would mean that it's changing your graph in the vertical direction. So like the outputs, the Y coordinates are changing. So that would be something like moving your graph up and down, flipping your graph over the X axis, or stretching or compressing your graph vertically. Versus horizontal. So that would mean shifting your graph to the left or right, reflecting it over the Y axis, or stretching it or compressing it horizontally. So making it wider or narrower. And so the way that you can determine whether your change is going to be vertical or horizontal is just by looking at, are you making a change to f of x or to x? So are you changing the function as a whole or your input? So for example, if you have a situation where you are adding or subtracting a number to the entire function, well, we know that addition and subtraction corresponds to a shift, and because it's being added to the function as a whole, it's going to be a vertical shift. Whereas if instead you're not adding or subtracting to the function as a whole, you're adding or subtracting to the input variable, well, that's going to be a horizontal shift. And so similarly for the other operations, negation and multiplication, depending on whether you're doing them to the function as a whole or to the input, that's what will tell you whether it's horizontal or vertical. So, I think in the topic of transformation, sometimes people feel like there's a lot of different things to memorize. I really wouldn't think about it like that. I think if you know how to tell whether something is vertical or horizontal, and then you know how to tell whether it's a shift, a reflection, or a stretch or compression, those are just kind of two different things that you can use to categorize any transformation. Okay, so what really is like the point of transformations? I would say it's to be able to take a function that is a little bit more complicated and to be able to compare it to a more familiar function that you know what the graph looks like. So for example, this function, so h of x is equal to negative x plus 1 squared plus 3. So what graph does that seem most similar to? Like what is the basic standard familiar graph that this is a transformation of? Well, it's a transformation of just f of x is equal to x squared. Right? That is kind of our basic function that we're adding and subtracting and negating from in order to get a new formula. And so now all we need to do is basically just look at this formula and see what are the changes and how are those going to show up in the graph. So first thing we might notice is that we have a negative sign. Now notice that the negative sign is outside of these parentheses. It's not directly on the x. And so that is what tells us that this is a vertical transformation. So this is going to be a reflection, right? Because it's a negative sign, and it's going to be a vertical reflection because it's not being applied to x, it's being applied to the function as a whole. So a vertical reflection is another way of saying a reflection over the x-axis. So we'll see that when we do this reflection, the y coordinates are going to change and the x coordinates will stay the same. So that's why I'm calling it a vertical reflection. Okay, what else do we see? Well, we see that we're adding a number to x. And so adding or subtracting a number is always going to be a shift. And because we're adding it to x, it's going to be a horizontal shift. And horizontal shifts are a little bit funny, and this is actually true for horizontal transformations in general, except for reflections. Horizontal shifts, as well as horizontal stretches and compressions, they work a little bit backwards from what you would expect. So I'm not going to really get into that, but definitely check out the 141 video that I'm linking below about shifts. In that video, I go into more explanation for why horizontal shifts work the way they do. But yeah, bottom line is that adding 1 to x, you might think it would shift it to the right, but it actually is going to shift it to the left. So horizontal shifts go kind of backwards of what you would probably expect. On the other hand, here we're adding 3, so we're adding a number, so it's going to be a shift, but this time we're not adding it to x, we're adding it to the function as a whole, and so this is going to be a vertical shift. And vertical shifts are a little bit more straightforward, they kind of work the way you would expect, and so in this case, plus means up, it goes up by 3. Okay, so how do we put this information together to actually sketch our transformed graph? Well, I'm going to start by just roughly sketching the graph of f of x is equal to x squared. So you want to put kind of a few key points on that graph that you'll keep track of as you do the transformation. So here is the graph of f of, struggling to draw this well. There we go. So this is the graph of f of x is equal to x squared. Now there is one thing we need to keep in mind when we do these transformations, which is that there is kind of an order of operations. So horizontal and vertical transformations, they just don't impact each other. So the order in which you do those just doesn't matter at all. What does matter is that if we have a vertical stretch or a vertical reflection, as well as a vertical shift, we have to do the stretch or reflection first, basically because of order of operations, right? Multiplying by -1 is multiplication. Multiplication happens before addition. So it is definitely possible to do all of three of these kind of at once without drawing like a middle graph, but just to make things simpler, maybe let's draw first what the graph would look like just with the vertical reflection, and then we can do both the shifts together to sketch the final graph. So a vertical reflection would mean we're reflecting over the x-axis. And so that means that all of the y-coordinates of our points are going to become the opposite sign of what they originally were. So in this case, they all become negative. And then notice the x-coordinates are all staying the same. It's like the x-coordinates are staying the same and the y-coordinates are flipping sign, and that's because it is a vertical reflection. A vertical transformation is never going to affect your x-coordinates, it's only going to affect the y-coordinates. Okay, so that is our reflected graph. Now we want to shift it to the left 1 and up 3. So we can take each of these kind of key points and just move them left 1, up 3. So left 1, up 3, left 1, up 3, left 1, up 3, left 1, up 3, left 1, up 3. And then we can connect the dots, and that is our final graph. That is the graph of h of x. So that's basically how transformations work, right? It's looking at your formula, making a comparison to a familiar function, and then figuring out what changes you need to make to the graph to reflect the changes in the formula. So let's do one more. So this one is h of x is equal to 2 times the square root of negative x. So which familiar graph is this a transformation of? So this is just a transformation of f of x is equal to square root of x, right? And by the way, and of course this always is true, but definitely feel free to pause the video and try this out yourself. See if you remember how this works. Okay, so what kind of changes are we making in this case? Well, here we see we're multiplying by 2, and so we know it's going to be some kind of a stretch or compression. Notice that we're multiplying the whole function by 2. It's not like we're just multiplying x by 2, right? If you just multiplied x by 2, then it would be a horizontal stretch or compression. But we're multiplying the whole function by 2, and so this is a vertical stretch. As I mentioned, vertical transformations work exactly how you would expect. So multiplying by 2 is going to stretch it by 2. We'll see that horizontal stretches and compressions work a little backwards. That's something we'll get into in our next video. Other transformation we see is that we're negating, right? We have a negative sign, and that negative sign is being applied just to x. It's not out here. If it was out here, it would be a vertical reflection, but because it's just on x, this is a horizontal reflection. And so a horizontal reflection means we're going to be reflecting it over the y-axis. So the x-coordinates are going to change sign while the y-coordinates stay the same. Okay, so just like we did with the last one, let's start by sketching our basic graph. So f of x is equal to square root of x. That's another graph that I would expect that you're familiar with by now. So it's going to look something like this. So again, just picked a few kind of key, easy points that we're going to keep track of. Okay, so in this case, you could do them one at a time, but really we can just do them all at once. I think especially when there's only 2 transformations, it's not that bad to kind of just do them at the same time. So stretching vertically by 2 is going to take each of our key points and multiply the y-coordinate by 2, right? It is a vertical stretch. Just want to label this. It is a vertical stretch, so we should be multiplying the y-coordinates by 2 while leaving the x-coordinates the same. But then we're also reflecting over the y-axis. So we're going to kind of stretch the y-coordinates by 2, but then flip the x-coordinates. So for example, maybe let's start over here with the point that was originally at 4, 2. If we take this point and we multiply the y-coordinate by 2, it would end up here. But then we also want to reflect it over the y-axis, and so at the end of the day, it would end up over there. So the y-coordinate changes from the stretch, and then the x-coordinate changes from this reflection. And then the point that was originally at 1, 1, if you multiply the y-coordinate by 2, it ends up at 1, 2. And then reflect over the y-axis, and it is negative 1, 2. And then finally, the point that was originally at 0, 0, well, if we multiply the y-coordinate by 2, we get 0 still. And then if you try to reflect that over the y-axis, it's actually still 0. So this point stays exactly where it was. And so our final graph looks something like this. So this is h of x. So yeah, I guess what I would say is part of the purpose of transformations is it allows you to sketch a graph without having to make a big table of a bunch of points. It allows you to kind of use what you know about simpler, easier functions to sketch the graph of a more complicated function. So that's exactly what we're going to be doing now with trigonometric functions, so with sine and cosine. So we're going to be focusing on starting with the basic graphs and then seeing how those graphs change when we make some changes to the formulas. Okay, so here I have, as usual, or we've seen these before, the graphs of sine and cosine. So this is f of t is equal to sine of t. This is g of t is equal to cosine of t. So hopefully at this point you're somewhat familiar with these graphs. Couple things I just want to remind you of that will kind of help us in this video as well as in the next video is remember the kind of key points. So I would say that basically the x-intercepts and then the maximum and minimum points, those are the most important points to be aware of. And those are also the easiest points to calculate on the unit circle, right? Because you don't have to draw a right triangle to do something like sine of pi over 2 or sine of pi or sine of 3 pi over 2. They're really quick to identify on the unit circle. And then similarly on cosine, we would have these 5 points. Another thing I want to point out is the symmetry that we see in these graphs. And so what I mean by symmetry is that, so looking at the sine graph to start, if we look at the beginning and end of a cycle, so 0 and 2 pi, the x-intercept in the middle happens exactly halfway between, right? It happens at pi, which is exactly halfway between 0 and 2 pi. And then if you look at the maximum point, that's at pi over 2, that happens exactly halfway between 0 and pi. And here, again, the minimum point, that happens exactly halfway between pi and 2 pi. And then similarly with cosine, the minimum point happens exactly halfway between the beginning and end of the cycle. So 0 and 2 pi, halfway between those is pi. And then these x-intercepts happen halfway between the minimum and maximum, right? So here and here, halfway between them, we find an x-intercept. And then if we look at the min and the max, halfway between those, we find an x-intercept. So this isn't going to come up so much today. It will definitely come up in the next video, because what's going to happen in the next video is we're going to be looking at horizontal stretches and compressions, and those are going to change the period of the function. And so it's kind of easy to lose track of where points are ending up. But if you remember these halfway rules, it will really help you sketch the graph. So one last thing I want to say is that these are not the entirety of the graphs of sine and cosine, right? This is just one cycle. And so typically when we're doing transformations, we're usually just going to focus on sketching one cycle, because if you know how one cycle looks, you could sketch the rest, right? Because the rest is just going to keep repeating that same pattern. Okay, so like I just said a moment ago, we're going to get into horizontal transformations in the next video. This video is going to be focusing just on vertical stretches and reflections and vertical shifts, which I think are a little bit easier to work with than the horizontal stuff. Okay, so first up we have a question asking us to sketch one cycle of the graph of h of t is equal to sine of t. So let's start by just drawing the graph of regular sine of t, so f of t is equal to sine of t, just so we can kind of have that right here as a reference. So I'm just putting in those 5 important points. Oops, let me make sure I make this curved. Okay, so that's the graph of f of t is equal to sine of t. So h of t is equal to 2 times sine of t. You know, that's a transformation of sine of t. And what kind of a change is going on here? Well, we're multiplying the whole function by 2. So multiplying the whole function by 2, multiplication we know corresponds to a stretch or compression. And in this case, it is a vertical stretch. And as we mentioned earlier, vertical stretches work the way you'd expect. So multiplying by 2 stretches the graph by 2. And so that means that all we have to do is take our 5 key points and basically double the y-coordinate. So the points that were originally at 0 are going to stay at 0. And then the points that are at 1 and -1 will be at negative or at 2 and -2. So our function will look like this. So one thing that I want to be able to describe here is how did the shape of this graph change? So because it was stretched vertically, the period didn't change, right? So the period is the length of the cycle, but it did change vertically. And so I want to describe some vocabulary that we'll be using to, or establish some vocabulary that we'll be using to describe the shapes of the sine and cosine graphs. So the first word I want to introduce is the midline. And so I'm not going to write down a definition because I think it's just easier to kind of see it in the picture. The midline of the trig functions of sine and cosine graphs is basically just what it sounds like, right? It's kind of the halfway point vertically. So for sine and cosine graphs that have not been shifted, the midline is always going to be the x-axis. So y is equal to 0. And I'll write that down in a moment. But basically, it's just, you know, halfway in between the highest and lowest point, right? It's the place that the graphs kind of start from and go back to at different points. That's the midline. Okay, another word we need to know is the amplitude. So the amplitude of a trigonometric function or of a sine or cosine function, that refers to, it's basically a way to describe the height, but it's not the entire height. It's kind of half of the height. And so the way that we can describe half of the height, it's going to be the distance from the midline to either the maximum or minimum point. It doesn't matter which way you measure, you'll get the same thing. So the amplitude is the distance from the midline to the maximum or minimum point. And so in this picture, the amplitude is basically this distance. So that is the amplitude. So as I mentioned, you could also measure it here. This is also the amplitude. But you know, it doesn't really matter which part you're measuring. The amplitude should always be a positive number because it's a distance. So it's just a measurement of the distance. So for a sine or cosine graph that has not been stretched, the amplitude is just 1. And then the last thing, and we've already defined this before, but I'll just write it down again, is that the period is the length of one full cycle. So in this case, you know, these graphs are kind of showing a lot going on, but if you were to focus on just one cycle of the graphs of sine and cosine, we've seen that that one cycle happens between 0 and 2 pi. So 1 cycle, the period is 2 pi. So this is the period. And one thing that I think is maybe worth noting is that the amplitude is like a vertical distance, right? So amplitude is a vertical measurement. And so what we'll see is that the amplitude is affected by vertical stretches, whereas the period, that is a horizontal measurement. And so we'll see that in this video, the period is never going to change in any of our examples because we're not going to be doing any horizontal stretches or compressions in this video. So let's just quickly write down what the amplitude, midline, and period are for the basic trig function. So for just sine of t and cosine of t without any kind of transformations. So for those two, the midline is just going to be the x-axis, so y is equal to 0. The amplitude is just going to be 1, because 1 is the distance from the midline up to the maximum height or down to the minimum height. And then the period, as we discussed, is 2 pi. Okay, so from here on out in the rest of the video, we're going to be using those same words to describe all the graphs that we come up with. So in this case, we can see that the amplitude is equal to 2, right, instead of 1. So because of the vertical stretch by 2, now the distance from the midline to the maximum point is actually 2. So the amplitude is 2. Okay, so we're just going to do a couple more examples in this video. And like I said, in the next video, we'll get into some kind of trickier examples. So this one is asking us to sketch one cycle of the graph of h of t is equal to cosine of t plus 1. So let's start by just sketching the graph of cosine so that we have that as our reference. So if you just had our g of t is equal to cosine of t, it hits its maximum at 0 and 2 pi, right? That's up at a height of 1. And then it hits its minimum halfway between those, so that's at pi. And then it goes through the x-axis, or the t-axis, I guess, halfway between those. And so our graph is going to look like this. So this is our original function that we're transforming. This is just f of t is equal to cosine of t. Okay, so if we have h of t, actually let me use a different color. I'll use this. So if we have h of t is equal to cosine of t plus 1, what kind of transformation is taking place for this function? Well, we're shifting it up by 1. And so we're adding 1 not to t, but to the function as a whole. And so that tells us it is a vertical shift. And specifically, it's a vertical shift up by 1 because vertical shifts kind of work the way you would expect. And so all that means is that we want to take our graph and just move all of our points up by 1. And one thing that can be nice to do with these is before you start moving the actual graph, you can think about where is the midline going to end up. So the midline, instead of being at 0, the midline is now going to be at y is equal to 1. Right? Because if we take the whole graph and shift it up, well, then the midline should also shift up. And so by doing that, that can kind of just like ground your graph. It can help you like see contextually, like where should things end up? Or you can just shift each point up by 1, but it's the same idea. So basically what we'll see is just like in the original graph, the maximum points, now they're at 2, but they still happen at 0 and at 2 pi. The minimum point now happens it still happens at pi, but it's at a height of 0 because it's been moved up by 1. And then those places where the graph crosses the midline, those are still going to happen halfway in between. So like here and here. And so our graph is going to look like this. So that is our graph of h of t is equal to cosine of t plus 1. What is the amplitude for this graph? So maybe I'll write this below instead of trying to fit it on the graph. So what is the amplitude? Well, the amplitude is still 1, right? The amplitude is the distance from the midline to the highest point on the graph. And so that is still a distance of 1. So even though we shifted the graph up, that did not change the amplitude. So amplitude is basically a description of the shape of the graph in a way, right? And when you just move a graph up and down, you're not changing its shape. So in this case, the midline did change, but the amplitude did not. And then also the period did not, right? The period is still 2 pi. We didn't do anything horizontally, so there's just no way that the period would change. And same thing with this one. The period is still 2 pi. So I want to do just one more example. And this one is going to have just a little bit more going on. So it's h of t is equal to -2 sine of t minus 1. So this is going to be a transformation of f of t is equal to sine of t. So I'm just going to start by quickly sketching that graph. And I think ideally you want to get to the point eventually with these where you don't always have to kind of draw the original trig function as a reference. If you are familiar enough with the general shape, you should be able to kind of remember how things go, right? But I'm just putting it here just kind of as a reference, especially because we're just starting out with this unit. Okay, so what kind of transformations are going on in this example? Well, we can see that we're applying a negative sign, not just to t, but to the function as a whole. And so that tells us that we're having a vertical reflection. So a vertical reflection would mean a reflection over the horizontal axis. And so let me just quickly sketch what that means about our function. It means that the basic shape that we're going to be looking for, it's going to have some other transformations, but the basic shape we're going to be looking for, instead of going up and then down the way that the typical sine graph does, our function is going to go down and then up. And so we'll want to keep that in mind when we get around to sketching our graph, as that goes down and then up. All right, what other changes do we see happening here? Well, we can see that we're multiplying by 2, and we're not multiplying t by 2. It's not 2t. It's the whole function getting multiplied by 2. And so that tells us that it is a vertical stretch. And specifically, it's a vertical stretch by a factor of 2. So that means that all of the y coordinates are going to become twice as large. And then last thing we can see is that we have a subtraction of 1. And so adding or subtracting is always a shift. And in this case, because it is being subtracted not just from t, but from the whole function, it is a vertical shift. And specifically, it's a shift down by 1. Okay, so I want to approach this one a little bit differently than we did the last ones. So, in the last ones, we basically applied our transformations to each point, right? So we had kind of our 5 key points and we applied the transformation. And then after we did that, we established what the midline and the amplitude were. And so what I think is a kind of a better method as we get more complicated, and so this is especially going to be true for the next video. So the next video, we're going to get into some examples that start to get a little bit complicated, a little bit potentially confusing. I think if you can first figure out what the amplitude and the midline and the period are before you start drawing, that will give you kind of this scaffolding. It will give you kind of a blueprint for where your graph should fit. And as long as you know the general shape you're looking for, if you have that kind of guideline of where the graph should fit and you know the general shape, you can put those two things together to sketch the graph without having to be so focused on exactly what's happening to your specific points. Okay, so what would the midline be for this graph? Well, if we're taking our graph and we're shifting everything down by 1, the midline should end up at y is equal to -1, right? Just like how in this example we shifted it up and the midline ended at y is equal to +1. All right, what about the amplitude? So we've seen that the amplitude is it's a vertical measurement, right? And it's a measurement that kind of corresponds to the height, not the whole height, but like half of the height of the function. And so the thing that is going to change the amplitude will be a vertical stretch. So just like in the first example we did here, where we stretched it vertically by 2, we saw that the amplitude became 2. The same thing is going to be happening for this function. So the amplitude is going to be 2. And then the period, as I've mentioned a few times now, the period is not going to change for these graphs that have not been affected horizontally, but let's just still write it down. Okay, so I'm going to put these pieces of information onto our graph, again, to kind of serve as like a guideline for sketching our graph. So there's our midline. Because the amplitude is 2, we can use that to figure out where the maximum and minimum height of this graph are going to be. So the maximum is going to occur at a height of 1, right? Because we're just going up from 2, or up by 2. So here's our amplitude, right? We're going up by 2 from the midline to get our maximum height. And then similarly, we can go down by 2 from the midline to get our minimum height. And so for me, I find this very helpful because this now kind of shows me exactly where the graph is going to live. You know, where is it going to kind of start out? What's the maximum height it's going to hit? What's the minimum height it's going to hit? And so now we're ready to sketch our graph. So we know that the original function, just f of t is equal to sine of t, that function has its y-intercept at 0. So because the midline has been shifted down, instead the graph is going to kind of start at -1. We also know, because of symmetry, that the graph is going to return to that same height at pi and also return to that same height at 2 pi. Okay, and so now we just need to think about what are where are the maximum and minimum points going to occur. And so this goes back to the reflection. Remember, because of the reflection, this graph is going to go down before it goes up. And so we're going to first go to the minimum point. Again, remember that the minimum is always going to happen halfway. Like, there's always symmetry. And so we know that our minimum height is going to be down here. And we also know that it's at a height of -3 because that's what the amplitude told us together with the midline. And then we also have our maximum up here. And so now we can just connect the dots and get our graph. So if you did this point by point, if you instead just focused on applying all the transformations to the 5 points, that would be okay. But like I said, I think when things get more complicated in the next video, you're going to find this method of kind of establishing your midline and amplitude and period to be pretty helpful. All right, so I'll see you all in the next video. Like I said, it'll just be more transformations focusing on horizontal transformations, as well as kind of blending together all the different transformations. So I'll see you then.